Our talk, as said, is called C2F2, a framework for detecting C2 frameworks at scale. This is a joint work by me, Oleg Boyarchuk, and my colleagues Sebastiano Mariani, Stefano Ortolani, this is the guy, and Giovanni Vigni of VMware's Threat Analysis Unit. Before we dive into the details of all this, let's find out what is a C2 framework and why do we care about them. Command and control, or C2 frameworks, are systems used to control and manage and maintain access to compromised devices. It used to be called backdoors back then. Do you remember Back Orifice 2000? So some may argue, but I believe it sparked the creation of C2 frameworks back then. C2 frameworks are widely used by cybercriminals, and the statistic says that the number of C2 servers is growing year by year. From financially motivated gangs to state-sponsored groups, everyone is enjoying the flexibility and polymorphism of C2 frameworks. And this is why we're working on it. I have 3 points. Polymorphic evasive implants, generation of large-scale databases of those implants, and machine learning-based detection. While work on detection of polymorphic executables has been done already, we haven't seen any research done on the polymorphic implants of C2 frameworks. Therefore, we decided to build a harness that automates this process, that creates implants automatically, and with thousands of samples generated, we decided to create a machine learning model that gives us the verdict whether a binary is benign or malicious. So basically, while normally cybercriminals are using polymorphic evasive implants to evade detection, we're flipping the tables on them by leveraging the same mechanism. Which C2 frameworks did we choose and why? We had 2 criteria. The first criteria is the C2 frameworks that we choose have to be either found in the wild or installed on Kali Linux or Slingshot VM. Take a look at this table. There are 10 C2 frameworks that we've chosen, and 8 out of them are open source, whereas 2 of them, Cobalt Strike and Root-Ratel, are commercial C2 frameworks. We found them leaked on VirusTotal, and we found out that they're actively used by cybercriminals. The second criteria we had that a C2 frameworks that we choose had to have some degree of customization. So have a look at this figure where Sliver, in order to generate an implant, it supports tremendous amount of parameters, so tremendous amount of ways how you can make a sample different. While most of the C2 frameworks share a lot in common, let's now focus on some notable features. While, why would anyone use a certain C2 framework over the other? Cobalt Strike, Empire, and Covenant provide API that allows automation. Cobalt Strike has a very well-documented scripting language called aggressor script. Empire supports RESTful API through JSON-based HTTP requests. And Covenant, which is on this title, provides a UI where you can play around with the API and print out some parameters that are not in the UI, in the main UI, for example. And you see how the values in the UI on the left correspond to the values that outputs API on the right. So with the API, you'll be able to not only create and stop listeners, but obviously you'll be able to generate implants. That's what we needed. Implants of Sliver, Godot, and Merlin are implemented in cross-platform Golang, whereas implants of Metasploit, PoshC2, and Empire have their own implementation for every OS architecture. On the other side, we have BroodRatel, Covenant, and Cobalt Strike and Shadow implants that support Windows only. However, there are some third-party implementations available. For example, there is a third-party implementation for Cobalt Strike called Geekan. It's written in Golang and supports Mac and Linux. Another notable feature is Malleable C2. Malleable C2 profiles are allowed to change network indicators of an implant to disguise its communication and help it to blend in on target. So Posh C2, BroodRatel, Empire, Merlin, and Cobalt Strike allow to change those parameters that can bypass certain network detection scanning. Take a look at the left figure where we see that during the creation of an HTTP listener of BroodRatel, one may specify a custom user agent, highlighted in green, custom data that is added before and after the post request, highlighted in purple, and the URI, custom URI that can be also used, highlighted in red. And you see how these values on the left correspond to the intercepted traffic, to the values in the intercepted traffic in the right. So basically, the implant, after it's been built, is using these parameters to, it may try to look like a browser, for example. Implants of BroodRatel, Posh C2, and Merlin, and Shadow can evade detection. Here I'm going to split them into two subgroups. BroodRatel, Posh C2, and Shadow implement their own custom evasion techniques, whereas implants of Shadow and Merlin, they rely on Donut to evade detection. And what is a Donut, you might ask? Donut is a framework that allows to create position-independent code to execute the code you need. So we basically feed the framework the implant that you've created, and it will create a shell code for you that you may execute from anywhere you like. So the left figure shows us a sample of an AMSI patching done by Donut. So basically, if one of the Shadow and Merlin implants run on the system, it patches AMSI. That stands for Anti-Malware Scanning Interface on Windows. And you see whenever an EDR that is relying on AMSI tries to scan the code that's being executed on the system, it will see and hear nothing because the beginning of that function is patched with an empty stub that always returns AMSI result clean. And the right table shows us the extensive out-of-box evasion capabilities of BroodRatel. You see how big the list is, and the author of that framework is releasing it, adding new capabilities with every release. Empire, Sliver, and Metasploit have massive libraries of built-in tools. So Metasploit is probably the world's most known and widely used penetration framework. Left figure shows how an attacker is using the Eternal Blue exploit to then later get the Meterpreter prompt at the end. So Meterpreter is one of the payloads of Metasploit that we also used during our research. The right figure shows how an attacker is installing the C2TC domain info package with the help of Sliver's Armory command. Armory is Sliver's extension package manager that contains even more, hundreds of more tools like that. So for example, with the help of this package, an attacker is scanning the Active Directory domain information during reconnaissance. And obviously there are some more packages too for lateral movement, for password extraction, etc., etc. Every now and then you see a quirky feature that a C2 framework supports, and which sometimes makes you wonder whether you should switch, that useful they are. Sliver, for example, embeds DNS canaries in implants. Shadow can mirror any site in real time. Covenant supports dynamic compilation of commands that are sent to implants and new implants themselves. So basically, the implant is very tiny that is running on the system, and in order to execute something, it executes everything on host and then sends the package to execute to the implant. Merlin supports domain fronting, and Godot, Cobalt Strike, and BruteRotel support DNS over HTTPS. I'll quickly cover just a couple of them. DNS canaries, top right figure, are deliberately non-obfuscated domain names that Sliver embeds in the binary, which, if ever resolved, will give a notification to the attacker that this particular binary was found. Domain fronting, bottom right figure, is the way to hide a malicious domain name within the encrypted HTTP traffic while resolving a benign domain name. So imagine you're resolving google.com, and then in the host HTTP header, you specify youtube.com. So basically, the communication starts with Google's IP address, and the Google will reply the YouTube's content to you instead of the Google's.com content. All right, enough of information enough of details of C2 frameworks. Let's finally dive into the details of the framework of C2 frameworks, as we call it, or C2F2. Here we have a generator that accepts input from the user that is then producing fully random implant configurations out of that input. That is later on sent by the submitter to the receivers. So from the submitter to the receivers, we have 10 receivers, one per framework, which is 10 in total, that are pulling config files from the queues facilitated by RabbitMQ and then sending them to the workers. Each worker can generate one implant at a time. And every worker in RabbitMQ is running in its own Docker container, which means the whole process is scalable and distributable. And obviously, everything that's been generated, such as the config files and the implants, are then stored in the storage of your choice. I'll show you a quick demo of the config generator in action. After installing the framework, you'll find a bunch of scripts starting with C2F2. So C2F2 generate implant configs, as the name suggests, generate configs. It accepts 3 parameters: the name of the framework, the number of configs to generate, and the output folder. You see it quickly generates 10 config files, and here I'm printing the first 3 to show you that they're fully random. Take a look at the address. The first 2 configs have the IP addresses, and the third one has a random-looking domain name. So these are configs like these were used during the generation of all those implants. So what's behind the config generation process, and what's also behind the every worker? We have 10 classes, 1 per C2 framework, that is, everyone is holding configuration parameters of that specific framework. So code highlighted in blue, do you see the blue one? It's really hard to see. So the top basically is the list of parameters that is supported by this C2 framework. Code in green with the synthesize function in the bottom packs all these parameters together and produces a configuration for the framework in the format that this framework accepts. Every class is relying on Pydantic, which is the most widely used data validation library for Python, Pydantic. So during the config generation phase, it generates random values of the config, And during the validation phase on the worker side, it validates the config that the script that pushes the config to the worker sends. And this is the exact code that had been running in the previous slide. Now I'm going to show you the submitter, receiver, and worker in action. So everything all together. You have two console windows here. The top one, the blue one, is where we are running a Docker container with the BrootRatel generator that generates implants and a RabbitMQ container. And the bottom one is where we are executing a script that is pushing the config to the worker. You see the Docker containers in the top start. In the bottom, I'm pushing the config to the worker. And you see receive job, blah, blah, generating implants. The generation process has started. And at the end, you see in the top created zip file for job has error equal false. That means there was an implant successfully created. In the bottom console, I'm going to print out the information that is stored within the resulting result.zip file. It is holding a bunch of logs and config files and the implants. There is another tar archive in the zip file, which after unpacking is holding all the implants that we have. So I previously said that every worker is generating only one implant at a time. So this time, we asked BrootRatel to generate all implants available of many different configurations. So what did we learn after we automated the creation of implants for all those C2 frameworks? As I already said, that Empire, Covenant, and Cobalt Strike provide documented API. But really, Empire's and Covenant's documentation is very limited. Therefore, we had to experiment a lot. So really, only Cobalt Strike was really straightforward to automate because of its well-documented scripting language. The good news are that 7 out of 10 frameworks that we had are command line interface based. Therefore, it's pretty easy to automate them with the help of Python's packages such as subprocess, PWN tools, or pexpect. Take a look at the right top figure where it shows that in order to generate a sliver implant, one needs to issue only one command, generate, with parameters, obviously. And after a little bit of waiting, this time it actually took 3.5 minutes, you see an implant being dropped on disk. That's how easy it is. On the other side, we have Covenant and BrootRatel that required a little bit of reverse engineering. Not a little bit, actually, a lot. So the bottom figure shows that in order to generate an implant for BrootRatel, one needs to first create a profile for that implant, then to issue a command to generate a new implant, and after a while, the server replies with the base64 encoded implant. And here I'm not even talking about double authentication process, which you have to go through by basically re-implementing the client-server communication that the client is normally doing. With the help of C2F2, we were able to generate thousands of samples. And based on the research that we found that allowed detecting executables, that allowed to create a machine learning model that operates on raw bytes, we decided to build our own model. And this is the model that we came up with. It is inspired by the malconf model from the 2017 report called Detecting Malware by Eating a Whole EXE. The goal of this model was to identify whether a binary is malicious, and it belongs to a certain C2 framework, or it is benign. And let's finally go through the whole thing and focus a little bit on every stage of it. This is our input data set. We have generated around 1,000 C2 implants, so per C2 framework, which is around 10,000 in total. On top of that, we had around 2,000 benign executables collected from various OS installations and 1,000 malicious executables that we accumulated on our customers' networks and found on VT. So the input data of the model is the raw binary. It is taken as is without any processing. So we take the raw bytes of the binary, including the P headers. So 512 kilobytes is the size of the input of our model, which is covering almost every sample that we had in our database. So the bigger files were cut, and the smaller files were padded to extend them to 512 KB. To every byte of the input, we apply byte2vec that produces a representation of the byte's value. So byte2vec produces representation of the byte's value, the position of the byte within the binary, and the values of the surrounding bytes. It outputs 512K vectors, which are then later on sent to a convolutional neural network. So here in the middle of our model, we have a CNN, convolutional neural network, that inputs 512K embeddings and outputs 1K by 100 values. So we had to reduce dimensionality of the output because we have another neural network, which I'm going to talk about a little bit later, which is heavy on processing. So therefore, we had to reduce the dimensionality. It processes 512 embeddings in one go with a stride of 512. So all these values were derived from experiments, 512 and the output size. At this stage, we have transformer encoder that captures sequential features. So the previous neural network CNN works best on sparse data, whereas this neural network works best on sequential features, on sequential data, and it does not change dimensionality. It just passes information through and outputs 1K by 100 vectors. At this stage, with the help of dense layers, we had to convert 1K by 100 embeddings to the notation of the classifiers. At the semi-final stage, we have classifiers that we use to classify the output. So they basically output a vector of probabilities that say whether a binary is malicious, benign, or belongs to one of those C2 frameworks. And all the values, all the probabilities are packed into one verdict. This binary is benign, and it is Cobalt Strike. Evaluation results, very important. So by looking at this graph, you might think that this is overfitting, but for our data set, we used samples that contain totally different configuration. Therefore, we can assume that the model is generic enough and it is not overfitting. This concludes my research, and I'd like to draw two conclusions out of it. C2 frameworks can be leveraged against themselves, while normally cybercriminals are using generative polymorphic nature of C2 frameworks to evade detection. We can leverage the same mechanism against them by generating large scale of databases of those exact implants and then training a model that will be able to detect them. And the second point which I'd like to make is OS architecture independent detection is possible. We have proven that it is possible to build a robust deep learning model that operates on raw bytes of the binary. And it does not require processing anyhow. So imagine BruteRetel comes up with an update and it says that it supports now macOS and Linux binaries. So it will not require too much effort to tweak our worker a little bit, generate 1,000 more macOS binaries, retrain the model, and deliver it in production quickly. That concludes my talk. Thank you very much. I really appreciate it.